Hello, everybody. I'm Niloofar Saeedzadeh Khaanghah from the Free University of Bozen-Bolzano in Italy. Today, I'm going to present my work on a stone-based substrate for thin film thermistor temperature sensors. First, I would start with a brief introduction to thin film electronic and temperature sensors in general. Then I would introduce the stone-based substrate that I use and go through the fabrication process. Then I would show the thermistor's performance, including electrical and mechanical analysis. And then I would end the presentation with a conclusion and a summary. In recent years, the advancements in thin film electronics technology have made possible the creation of innovative electronic devices and sensors that have interesting applications like being flexible, lightweight, conformable, stretchable, and obtrusive, and the possibility of being transparent and fabrication on large area. One of the important fields for thin film electronic is the temperature sensor. Because of its important role in healthcare, food industry, fire and safety, energy consumption, building automation, transport, and automotive. And this is where thin film electronic technology comes into play, because it's possible to fabricate temperature sensors directly on top of some unconventional substrates, that most of which are even environmentally friendly. So we have thin film electronics, we have temperature sensors. We want to bring these two together, but there are always some issues like environmental problem, poisonous materials, plastic pollution, recyclability. And what is my solution here is to use a stone-based material. In total, here you see I have 4 different stone-based substrates, which are more and more in like a processed stone. I have marble, which is a natural stone. I have the brick, which is a heat-treated stone. We can easily put it in the mold and have in different shapes. I have the stone paper and the Limex, which are based on polymer and stone powder. The stone powder used in these two materials is the limestone or calcium carbonate, but the difference is in the binding agent. In case for stone paper, it is high-density polyethylene, and for the Limex, it's polypropylene. The root mean square roughness for the Limex is 4.6 nanometer, but the other substrate materials were too rough for AFM measurement. The stone paper and the Limex are commercially available and are good alternative for conventional paper and plastics. And you know that we all have marble in our homes, in the kitchen, in the bathroom. So why not making them smart? Why not having some safety features in our kitchen, next to the oven, in our fancy homes? We also can have, because the marbles are also used in jewelries, we can also integrate sensors on our jewelries for biomonitoring. We can also have sensors on the tiles, directly on the tiles, to monitor the temperature of the floor, of the walls, not only monitor temperature of the environment. Also using the stone paper and the Limex, having smart wallpapers or having a smart packaging specifically for pharmaceutical application. I know we all can have more possible application, but having this motivation, we can move on to the next slide and talk about the fabrication. Here you see all the stone-based substrates that we load them in the sputtering vacuum tool to check their outgassing time. As you see here, all the substrate materials to reach the temperature of 2 - 6 millibar for the outgassing time, they all had less than, it took less than 15 minutes for all the substrate, which is quite manageable in a short time. So we took one by one the substrate in the sputtering tool main chamber. We used a kind of shadow mask to sputter copper to sputter metal contacts on top of the substrate. And to connect these metal contacts, we use another shadow mask and a sputtered InGaZnO semiconductor to fabricate the total thermistor, and this is how the thermistor looks like after the fabrication. And this is a real 3D image of the thermistors fabricated on the brick. And here you see all the thermistors on different 4 substrates ready to be analyzed. So talking about the performance, we took a similar circular pattern of the sensor. Here, the diameter of the sensor is 13.2 millimeter. We started with a current voltage characteristic to confirm that there is a nice ohmic contact between the copper and indium gallium zinc oxide semiconductor, also to confirm that they are conductive. Here you see the sensor performance. The plot shows the resistance variation versus the temperature. The temperature variation range is between 25 to 80 degrees. As you see, when we heat up the thermistor, the resistance goes down, and this is what we expect from a thermistor. We did 5 different measurements. That's where the error bars comes from. If you look, the 2 rigid substrates, the 2 rigid thermistors has smaller hysteresis comparing to the stone paper and the Limex thermistor. And by taking a linear approximation of the plots, we can get the sensitivity, and the sensitivity of the marble is larger from all the thermistors, and this is due to the high thermal conductivity of the marble thermistor comparing to the others, and also due to the nature of the stone paper and the Limex thermistors, because they are polymer based and we don't know exactly what happens by going to the higher temperature. Here you see the cycling plots just to check the stability of the signals. As you see, the marble is the most stable thermistor. The brick, there's a way, but still okay, and the other 2 are also somehow okay. And for these 2 flexible thermistors, also I did the bending measurements. As you see, the normalized resistance value for the Limex stays more or less the same. But for the stone paper, we have a slight increase by going from to the smaller bending radius. The maximum strain at the 25 millimeter bending radius is 0.37%. And also the stone paper stopped working after this maximum strain. And the difference is here, because of the different binding agent, the thermoplastic resin used in the material, because the polypropylene in the Limex is more flexible. Even by touching these 2 substrates, you can feel that the Limex looks like and feels like a plastic folder, but the stone paper is really more like a normal conventional paper. So there might be some micro cracks on the surface of the sensor that it stops working after this maximum strain. In conclusion, here I introduced 4 different stone-based substrates that are environmentally friendly. And I used copper and InGaZnO semiconductor, and with a sputtering tool, I fabricated thermistors. And as I checked the sensitivity of the thermistors, the marble thermistor has the higher sensitivity and also very stable signals. And the bending measurement for the 2 flexible thermistors showed that the stone paper thermistor slightly increased by going to higher strength. And thank you. And if there is any question.